Okay, so number one says if the null hypothesis is not rejected, that would be fail to reject HO, then there is strong statistical evidence that the null hypothesis is true. That's false. If it said if we have null hypothesis is rejected, we would have strong statistical evidence that the null hypothesis is false. That's because we set that alpha error to 0.01 or 0.05 or whatever. But now when we fail to reject HO, we would say HO may be true, not that we have strong evidence, just that it could be. And part of the reason we make that equivocation is that the probability of an error, the type of error, is a type 2. And that probability is not something we preset as part of the test. And so that beta error, the chance of error, could be 1%, 5%, or it could be 40 or 60%. So that's false. Number two, the hypothesis P1 equal P2 is equivalent to hypothesis P1 minus P2 is equal to 0. Well, that's true because if the difference is 0, that means they are equal. And I want to go ahead and also emphasize that maybe a little bit easier to think of it and say PA equal to PB. But when we get to our sampling distribution and either drawing the sampling distribution or thinking about it, the center of the distribution will be 0. And so it's kind of nice to have this formulation of PA minus PB or P1 minus P2 equal to 0. And I'll note also that the same thing holds true if your hypothesis concerned population means mu A and mu B. Okay, so number 3, the standard deviation of the distribution of x bar, that's the standard error of the sampling distribution, if it's x bars, decreases as n increases. So the thing you want to do there, if it doesn't just make sense to you, which I hope it does, this is true, but you could just write down the formula for standard error, and that is for a t-test where you have sample standard deviation s divided by the square root of n, or if you had population standard deviation sigma divided by the square root of n. At any rate, n is in the denominator, and so the larger that number gets, you're going to have a smaller value. So the standard error will go down, and so will the interval. The interval is just going to be z or t times the standard error. So assuming your level of confidence stays the same, if you increase the sample size, the width of the interval will decrease. For the standard error of x bar is s, well, you can see even from this screen that the standard error for the sample mean is sx bar, and that's not s, it's s divided by the square root of n, or s x bar would be the correct symbol to put for that. If you have a sample standard deviation. If you have population standard deviation, it would be sigma x bar. And so number 5, just please skip that. It's true, but I think it could lead, thinking about that, it could actually confuse a concept that I think is pretty important to know. So I think please just skip that one. Yeah, number 6, we're estimating a population proportion. Of course, we have our interval here, the statistic p hat plus or minus the critical value or the confidence coefficient z times the standard error. The question here is our sample size large enough? And as you can see where I have kind of written all this all out here, but so I'll kind of underline as I go through here. The rule is that both the yeses and nos have to be greater than 10. So you can't just look at this column where we have the sample sizes. You have to look at the proportion of yeses and nos, or really the number of yeses and nos, to make the decision. So in the first case here we had n is 20, p is 0.4, that was given. Well, if 40% of the sample of size 20 says yes, that's 8, and 8's not large enough. You don't really, that could be the end of the computation on that one, but if you took 60% of the 40% yes, 60% said no, 60% of the 20 would give you this 12, Or you could just take 20 minus 8 to get 12, because the number of yeses and nos have to add to n. And so for part B, it said 40 and 0.75. Well, 0.7 times 40 is 30. That's bigger than 10, greater than or equal to 10. And then 40 minus 30 is 10, or 25% of 40, if you want to think of it that way, is 10. So that'll be the answer in this one. Just moving down a little quickly here, so you can see the sample size is even larger, but the p-hat is 0.05, so 5% of 100 is 5. That's not greater than or equal to 10. And the next one's 150, and 5% of 150 is 7.5. That's not bigger than 10. And then even when you had 200, we have 0.96, so the number of yeses was 0.96 times 200, or 192. But that only leaves 8 no responses, and that is not greater than or equal to 10. So that's why that one is not large enough. Okay, the next question, which is one that quite a few people were having trouble with when we were going over this in class Wednesday night. We have a confidence interval. We're given the outer bounds of it, and it's given at 90%, and we want to know, well, which one of the following intervals would be a 95% interval? And I'm going to admit, at least in terms of the amount of math and that for one multiple choice question, maybe it's a little bit much. But let's take a look at what we've got going here. Okay, already done that. Okay, so let's start with what we have here. We have a lower and an upper range to the 90% confidence interval, and that goes from 0.573 to 0.787. So if we want to get the width of the entire interval, we're going to take this distance and get the width of the entire interval. The center of our interval is going to be the statistic p-hat, and this distance between p-hat and the upper limit, which will be the same distance as p-hat to the lower limit, is the margin of error. I've got all the math on the next page, but once we get this difference, 787 to 573, we'll take half of that distance. That's going to be MOE. And then that margin of error, whatever it comes out to be, let's see, I think I'll go ahead and just bring my calculator over here and calculate that here. We had 0.787 minus 0.573. So that's 0.214 for all of that. That means this is half that, or 0.107. So that's the margin of error. So we had the width, lower minus upper, divide that in half to get the margin of error. Now what we do also know is that the margin of error is going to equal z times the standard error. If you wanted to could write that out a number of ways, that standard error, you might call it sigma p-hat. Could write it out as the square root of p-hat q-hat over n. We really don't need any of that to work any of that out, but just in case you see it in other places. Well, z times the standard error is the margin of error. Well, right, with a 95% confidence interval, that's 1.645. And basically what we want to do is change that to a 95% confidence interval. So instead of z being 1.645, it's going to be 1.96. So if you're pretty good at math, you probably can already see what the easiest way to do this would be to take the 0.107 and multiply it by the ratio of the new z to the old z, 1.96 over 1.645. Let me go into my next page here. This is just some of what we just did just a second ago, or what I was talking about there. I've got my, because I didn't say one part of it, let me go back and show that on here, that if our margin of error was 0.107, and our upper limit was 0.787, then this p hat is 0.787 minus the 0.107, or 0.68. So that's p hat. So this one way of stating this whole interval will be to be, say, 0.68 plus or minus the margin of error of 0.107. Which is what I have here. So that 90% confidence interval, that 0.107 for 90% is equal to 1.645 times the standard error, and for 95% it'll be 1.96 times the standard error. And what we can do is just say we can take that to convert that. Maybe it might be a little easier for you to think of it in this way. I mean, I'm going to end up with what I'm here. For that right-hand side, I've got 0.107, which I know is 1.65 times the standard error. So I'm just going to take out the divide by 1.645. That'll leave me with the standard error. And then I'm going to just multiply that by 1.96, and that will give me the new margin of error. So this will be the margin of error for the 95% interval. And so what we'll have to do then is take our statistic, the 0.68, and plus or minus this 0.107 times the margin of error. Sorry, plus or minus the margin of error. So I think probably the best thing on this is just to go over it and just go ahead and put this on the calculator here. 0.107 divided by 1.645. That'll leave us with the standard error. Multiply that by 1.96 to get the new margin of error. And then all we need to do is take our original statistic, our p hat, 0.68, and then add and subtract that 0.127. So I'm just going to subtract 0.127, and then I'm going to second enter and just go change that to a plus sign. And so our answer should be 0.553 to 0.807, and that is our answer. It's C.